are going to test the convergence of P series. We are going to test the convergence of P series. The problem is, show that the P series, sigma I running from 1 to infinity, 1 by I raised to P equal to 1 by 1 raised to P plus 1 by 2 raised to P plus 1 by 3 raised to P plus etc. plus 1 by I raised to P plus etc. where P is a real constant, converges if P greater than 1 and diverges if P less than or equal to 1. Once more, show that the P series, sigma I running from 1 to infinity, 1 by I raised to P equal to 1 by 1 raised to P plus 1 by 2 raised to P plus 1 by 3 raised to P plus etc. plus 1 by I raised to P plus etc. where P is a real constant, converges if the series converges if P greater than 1 and diverges if P less than or equal to 1. Okay. Here we want to show that the given series, that is the P series, converges if P greater than 1 and diverges if P less than or equal to 1. Okay. The function f of x is equal to, here the function f of x is equal to 1 by x raised to P. Here the function f of x is equal to 1 by x raised to P. This function is continuous. This function is continuous and positive decreasing function for every x greater than or equal to 1. Once more, f of x is equal to, here f of x is equal to 1 by x raised to P. This function is continuous and positive decreasing function for every x greater than or equal to 1. And the ith term of the given series is f of I equal to 1 by I raised to P. f of I is equal to 1 by I raised to P. Here the ith term is f of I is equal to 1 by I raised to P. Clear? So here we are using integral test for testing the convergence of the given series. For let P greater than 1. But using integral test, integral 1 to infinity f of x dx is equal to, integral 1 to infinity f of x dx is equal to integral 1 to infinity, here f of x is 1 by x raised to P dx. That is equal to integral 1 to infinity x raised to minus P, limit b tends to infinity, integral 1 to b x raised to minus P dx. Okay. That is equal to limit b tends to infinity x raised to minus P plus 1 divided by minus P plus 1. Minus P plus 1 divided by minus P plus 1. 1 to b. Now we get integral 1 to infinity 1 by x raised to P dx is equal to 1 by 1 minus P, limit b tends to infinity, into 1 by b raised to P minus 1 minus 1. Putting it as equation number 1. Okay. Putting it as equation number 1. Here P greater than 1. Here P greater than 1. That means P minus 1 is greater than 0. P minus 1 is greater than 0. Then we say that B raised to P minus 1. B raised to P minus 1 tends to infinity as B tends to infinity. Here P greater than 1. That means P minus 1 is greater than 0. Then we say that B raised to P minus 1 tends to infinity as B tends to infinity. Then equation 1 becomes integral 1 to infinity 1 by x raised to P dx equal to 1 by 1 minus P, limit b tends to infinity, here 1 by b raised to P minus 1 minus 1. Okay. 1 by b raised to P minus 1 minus 1. Okay. Now applying the limit, we get 1 by 1 minus P. Applying the limit, we get limit b tends to infinity b raised to P minus 1 tends to infinity. That is here 1 by infinity. 1 by infinity is 0. 0 minus 1. Okay. That is equal to negative 1 divided by 1 minus p. That is equal to 1 by p minus 1. Negative 1 divided by 1 minus p, that is equal to 1 by p minus 1. Now we get integral 1 to infinity 1 by x raised to p dx is equal to 1 by p minus 1 when p greater than 1. Okay, here p minus 1 is greater than 0 because p is greater than 1, then p minus 1 is greater than 0. That means this is greater than 0. That is, it is a finite value. Then we say that the given series converges if p greater than 1. The given series converges if p greater than 1. Here we get integral 1 to infinity 1 by x raised to p dx is equal to 1 by p minus 1. P minus 1 is greater than 0. Then we get 1 by p minus 1 is a finite value. That means integral 1 to infinity 1 by x raised to p dx get finite value. Then we say that this integral converges. By integral test we say that the given series converges if p greater than 1. The given series converges if p greater than 1. Okay. Converges if p greater than 1. Okay. Now we get the given series, the p series converges if p greater than 1. Okay. Now we want to show that the given series diverges if p less than 1. Diverges if p less than 1. Okay. And 1. Then if p less than 1, then 1 minus p is greater than 0. 1 minus p is greater than 0. Then integral 1 to infinity 1 by x raised to p dx equal to, by equation 1 we can write it as 1 by 1 minus p limit b tends to infinity into 1 by b raised to p minus 1 is b raised to 1 minus p minus 1. Okay, that is equal to 1 by 1 minus p limit b tends to infinity b raised to 1 minus p minus 1. Okay, applying the limit we get 1 by 1 minus p into limit b tends to infinity b raised to 1 minus p minus 1. Okay, now we get limit b tends to infinity b raised to 1 minus p is infinity. Then we get this is infinity, that is integral 1 to infinity 1 by x raised to p dx equal to infinity. That means the integral diverges if p less than 1. That means by integral test we say that the given series diverges if p less than 1. Clear? Now if p equal to 1, then integral 1 to infinity 1 by x raised to p dx is equal to integral 1 to infinity 1 by, here p is equal to 1, then 1 by x dx, that is equal to limit b tends to infinity integral 1 to b 1 by x dx. That is equal to limit b tends to infinity 1 by x, integral of 1 by x is log x. Applying the limit 1 to b, we get limit b tends to infinity log b minus log 1. Log b minus log 1. That is equal to infinity. We get infinity, log 1 is 0 and limit b tends to infinity log b is infinity. Then we get integral 1 to infinity 1 by x raised to p dx is infinity when p equal to 1. If p equal to 1, this integral is infinity. That means the integral diverges if p equal to 1. That means the given series diverges if p equal to 1. Clear? Now we conclude that the given series converges if p greater than 1 and diverges if p less than or equal to 1. Clear?